Okay, next problem, number 36. We're given a scenario where we have an air-filled capacitor here with a distance between it of about 4 centimeters. A distance of about 4 centimeters. Sorry, I was just checking something. Just double checking. 4 centimeters here. And now what we do is we drop a ball that's charged, a sphere, right? And it's going to actually form an angle. That angle with the vertical is going to be 15 degrees. So something is happening here. The electric field in the capacitor is interacting with the charged sphere, and it's causing it to move in this direction, right? So we're told also that we have a 350 microgram sphere, which is just going to be 350 times 10 to the negative 6, 10 to the negative 9 kilograms. And its charge is 30 times 10 to the negative 9 coulombs, right? We want to find the voltage difference. So what we can do is we can sum up the forces in equilibrium. I mean, we're given a scenario where we have, we have a weight force, we have an electric force pushing this way, we have a tension force pushing that way, right? So let's sum up our forces and see what we get. Well, cosine, right? So we have the cosine component here. This is going to be Ft times cosine theta minus mg is equal to 0 because we're in equilibrium, right? So slowing down a little bit, we have the tension force. The y component of the tension force is pulling upwards. The magnitude of the tension force, cosine of the angle. We have the weight force pulling down here. So if we draw a force diagram, that's kind of weird. If we draw a force diagram, we'll see more clearly. This is Ft. This is the weight force. This is going to be the electric force, right? Now, the tension force has y component, Fty. It also has an x component, Ftx. Okay? So that's where we're at. So this means, using this equation here, Ft is equal to mg over cosine theta. Doing the x components, we have Ft sine theta. Let's see here, what do we got? Minus Fe. So the way I drew this diagram, you could actually redefine these. This could be positive and this could be negative, but it works out the same either way because I'm just setting these in equilibrium. So what I'm saying is we now have Ft. Ft is equal to the electric force over sine theta, which is also equal to Q times the electric field over sine theta. Right? So now we also know that the magnitude is equal to mg cosine theta. Now what did we want to solve for? We wanted to solve for the electric potential difference. Right? So we're going to want it in terms of E. Okay? So then let's set these equal to each other. I'm setting this equal to this. This thing that I found equal to this thing that I found. So Q times E over sine theta is equal to mg over cosine theta. That means that E is equal to mg over Q tangent theta. Okay? Now recall that the potential is the negative E times delta D. Right? So that's going to be mg over Q tangent theta times D. So then we plug everything in. 350 times 10 to the negative 9 kilograms times 9.8 meters per second squared. That's gravity. acceleration, and then we got tangent of 15 degrees. Then we have 0.04 meters over 30 times 10 to the negative 9 coulombs. That's going to give us a value of negative 1.23 volts. Now this ended up being negative because of this identity. And I think we want to keep that. Let's just double check. Yeah, that's right. Okay,